You ever have one of those moments, you've spent hours on a program, it's finally running, and then bam, it crashes? All because of one single piece of bad data. It's so frustrating, right? Well, today, we're going to learn the Python techniques to make sure that never happens again. We're talking about building really robust code that can handle all the messiness the real world throws at it.
And this right here, this is the core of the problem, especially if you're in data science. You know the drill. You're trying to process a file with thousands of rows and just one unexpected text entry in a column that's supposed to be numbers, and your entire analysis just screeches to a halt. But you know what? It really doesn't have to be that way.
Okay, let's really dive into the difference here, because this slide says it all. Over on the left, you've got what we call fragile code. The second it sees something it doesn't expect, like trying to turn 10A into a number, the whole thing just falls over. Crash. But now, look at the right. That's robust code. It actually anticipates this problem, handles it gracefully, and lets the rest of your program just keep on trucking. That, my friends, is the power of exception handling. So how do we actually do this? Well, we start with the most fundamental tool in our kit, the try and except block. Honestly, the best way to think about it is like a safety net that you place under any piece of code that you think might, take a tumble. Let's get clear on what we're talking about here. An exception. That's just Python's fancy word for an error that pops up while your program is actually running. And our goal isn't to stop errors from ever happening. I mean, that's pretty much impossible. The real goal is to catch them and respond intelligently so the program can keep going. Now, it's really tempting to just use a generic except block that catches absolutely any error. But that's kind of like using a giant fishing trawler net to catch a single goldfish. It's total overkill, and worse, it hides what's really going on. By being specific and catching particular exceptions, you can tailor your response to the exact problem. Trust me, it makes your code 1,000 times easier to debug later on. So let's meet the usual suspects. Value error? Oh, you'll see this one all the time in data cleaning. It's what happens when you try to cram some text into a number format. Files and on error is pretty self-explanatory, but it happens constantly when scripts get moved around or data isn't where you thought it was. And zero division error? Well, that's just a classic math trap. If you can anticipate these specific errors, you can build much smarter, targeted ways to handle them. Okay, so the basic try except is a fantastic start, but we can add a lot more finesse. By using 2 more keywords, else and finally, we get way more control over our code's flow, letting us handle both success and failure with real precision. This right here is the complete roadmap. You always start with try. If something goes wrong, you immediately jump to the except block. But what if everything works perfectly? That's when the else block gets its moment to shine. That's your success code. And finally, that's the one part that is absolutely, positively guaranteed to run at the end, no matter what happened before it. And this is the main takeaway for finally. It is your absolute guarantee. It doesn't matter if your code worked, if it failed, or if you caught the error, the code inside finally is going to run. And that makes it incredibly reliable for those mission-critical operations. So why is this such a big deal? Well, think of finally as your code's essential cleanup crew. Let's say you open a file or you make a connection to a database. You have to close those things to free up your system's resources. If you stick that closing code in a finally block, you can be sure that cleanup will happen, even if some crazy error happened while you were trying to process the data. All right, so up to this point, we've basically been playing defense, right? We're reacting to errors that Python throws at us. But what if we want to go on offense? What if we want to create and trigger our own errors to enforce the specific rules of our application? We can totally do that. Okay, picture this scenario. What if the data you get is technically valid to Python, but for your program, it makes absolutely no sense? For instance, someone enters an age of -5. Python has no problem with the number -5, but we know an age can't be negative. That's a logical error, not a programming error. And the tool for this job is the raise keyword. It lets us stop the program and signal an error, but on our own terms. When our code spots a condition that breaks our rules, we can raise an exception, just as if Python itself had found the error. Let's see this in action with a simple setAge function. We're setting a rule here. Age cannot be negative. That if statement, that's our bouncer at the door. If an invalid age tries to get in, we don't just ignore it. We actively raise a value error with a helpful message. This stops the function dead in its tracks and prevents that bad data from ever getting processed. It's how we enforce our own logic.
Okay, the theory is great, but let's put it all together now. We're going to combine try, accept, and raise to build one single, super robust function that solves our original problem, processing a ton of messy data without crashing. So, our little mini project is what I'm calling a safe average calculator. Its only job is to take a list of values, which could be a mix of numbers and just total junk, and calculate the average of only the valid numbers. A fragile function would crash on the very first piece of text. Ours isn't going to flinch.
So here's the game plan. Part 1. We loop through every single item in our input list. Inside that loop, we wrap our number conversion inside a try block. If it works, awesome, we add it to our list of good numbers. If it fails, because the item is some random text, the accept value error block catches it, and we just pass, which is basically telling Python, hey, no big deal, just move on to the next one.
But wait, there's one more tricky edge case. What if the input list had no valid numbers at all? If that happened, we'd end up trying to divide by 0 later, which, yeah, that would crash. So after our loop finishes, we do one last check. If our list of numbers is empty, we go on offense and proactively raise a value error with a really clear message, completely preventing that 0 division error from ever happening.
And here it is, the payoff. We gave our function this messy list with numbers and text. A fragile function would have died instantly. Ours, it didn't even blink. It intelligently skipped the bad data, processed the good stuff, and returned the correct average. This is what we mean when we talk about robust, production-ready code.
And that really brings us to the final thought. Look, it's not a question of if your code is going to run into weird, unexpected, messy data. It's a question of when. Using these exception handling techniques isn't just a nice-to-have skill. It's absolutely essential for building programs that are reliable, resilient, and ready for whatever the real world throws at them. So the only question left is your code ready?